Hello everyone, my name is Ludwig. I'm the former project lead and one of the founders of Project WESP. WESP is the abbreviation for WARR Experimental Solid Platform, which we found 1.5 years ago because we had two very active projects, Project Cryosphere working on a hybrid engine and Project Nixus working on a biliquid engine. But as both of these rockets have been built around their engines and about their propulsion system, we needed something else to further develop our structural components as well as our aerodynamic components to also achieve higher velocities, because at those velocities, of course, the stress on those components is higher. Therefore, we've decided to build the first rocket of Project WESP, which was EX-1D, which you can see here, which had its maiden flight in April 2024. And afterwards, we reused the EX-1D rocket and used it as the booster for our Spaceport America Cup 2024 two-stage vehicle, which we called EX-1E, as we're still in the EX-1 series with solid rockets, but further develop incremental to building bigger and bigger systems. The whole rocket is made from carbon fiber, which gives us both a very lightweight solution as well as maintaining the high forces acting on the vehicle both during boost phase as well as during the recovery. The whole skins are wound from Toprec carbon fiber on the winding machine of the chair of carbon composites, thanks on this side. The skins are a few millimeters thick, but still they have enough power to withstand the 8 kilonewtons our low stage engine provided during the ascent. We will also make an additional video about those skins in the future, so make sure to hit the subscribe button to see that video as well. As the rocket we flew at Spaceport America Cup went supersonic, we needed to make sure that it's able to withstand the aerodynamic forces acting on the rocket while heating up not too much to exceed the material properties. Therefore, the tip of our glass fiber nose cone is made from aluminium, because the glass fiber itself wouldn't be strong enough to withstand these high temperatures during the high velocities we saw during flight. This recovery system sits in the cylindrical part of the nose cone and is set up as a two-stage recovery system with both a drogue and a main parachute to get the perfect balance between fast descent and therefore low drift with ejecting the drogue parachute at apogee, but still getting a slow touchdown velocity to make sure the vehicle is still intact and can be reused straight after the flight. The main parachutes was ejected at 500 meters height, making sure that our touchdown velocity was at roughly 5 meters a second. But also for that, we'll give you a better view over the whole recovery system from our recovery lead. So you will see that in the upcoming videos. Next up, we have the payload segment, which was in here together with cameras and antennas, where we had an experiment from our partner team WARR Space Labs, which developed an experiment measuring bioluminescent algae while the acceleration and vibrations of the boost phase, as well as during the descent under parachutes and of course during the coast phase without gravity. The experiment was water-cooled, which gave us quite some problems during the launch. Next, we have our electronics segment, where we had our self-developed flight computer. Together with the COTS flight computer we used as secondary flight computer as well as for the upper stage ignition, as the rules of SAC didn't allow us to ignite the upper stage with our self-developed flight computer. Besides that, we had the upper mount of the engine. We flew an M1939 during the competition, which propelled us to a little bit above Mach 1 and a height of 7,800 meters. which was on the lower stage mounted in a 3D printed aluminum part, which also incorporated the bow tail of the upper stage as well as the upper half of the staging mechanism. The staging mechanism is, of course, one of the most important parts for a multi-stage launch vehicle. Therefore, we had a whole sub-team only to develop this mechanism. We'll also give you a better insight in one of the next videos. The staging mechanism worked with 2 fitting surfaces, making sure that we have an overall fitting surface length of more than 1 caliber of the rocket, and still withstand all the forces acting during both integration as well as the launch, as the staging mechanism had to hold the weight of the full upper stage during launch rail erection. The staging mechanism is built completely passively. We had a few hundred newtons more drag force on the lower stage as on the upper stage. Therefore, the aerodynamic forces pushed the vehicle apart as soon as the lower stage engine didn't give us enough boost anymore to push the stages together. The staging mechanism, of course, is covered with an aerodynamic cover during the boost phase, but we removed this to make sure you can see all the nice details inside this staging mechanism. The cover was the second part made from glass fiber instead of carbon fiber, as we had our antennas of the lower stage sitting below it, and therefore we needed to make sure that the material used is radio transparent. As the material properties of glass fiber are not strong enough to withstand the forces we saw here, we had a load-bearing aluminum structure below, which made this section the only section of the rocket where the aluminum parts have been load-bearing, of course besides our structural connectors, but besides that we only use the carbon fiber skins as load-bearing parts. Next, we have our low stage recovery system, which we of course weren't able to set up as a nose cone ejection system, as there is no nose cone in a lower stage. Therefore, we newly developed a sideways ejection mechanism. The whole mechanism is only activated by rope cutters sitting in here. We have a small Kevlar string going through these holes and hold the hatch in place. And as soon as the rope is cut, the pressure the parachutes are packed with, right now we don't have the parachutes in here besides the drogue parachute, therefore the pressure is not that high. But when we have everything in here, the pressure really pushes out the hatch, making the aerodynamic drag push it even further, and therefore it falls off, pulling out the drogue of the lower stage, which gave us the chance to have a recovery system somewhere within the vehicle, so also closer to the center of gravity of the lower stage. Next, we have our lower stage engine, which was all the way up here until down here, as it propelled us with roughly 8 kilonewtons of thrust off of the launch rail. We had an acceleration of above 10 times the force of gravity acting on the rocket, which allowed us to have a launch rail provided by SAC instead of bringing our launch rail, which wouldn't have been able for us to bring to the United States as a European team. The motor in the lower stage is mounted through a 3D printed titanium part, which allowed us to transmit the forces acting here on the engine into the skin evenly while maintaining the lowest possible weight and giving us the optimized structure for it. The engine diameter we used is roughly 100 millimeters. We flew a Casseroni N5800, as we used the lower stage as a standalone vehicle earlier, so we needed to make sure that the engine is held in the center of the vehicle to align the thrust vector with the orientation of the vehicle. The fins we originally wanted to manufacture are should have been manufactured in the way we did it for our EX4B rocket, which we used for the IREC 2024. But due to time constraints, we haven't been able to manufacture this fin can for the SAC 2024 vehicle. Therefore, we used trapezoidal fins from a carbon fiber plate with sharpened leading and trailing edge just attached to the rocket through aluminum parts. Also in this section, as it is the lowest part of the vehicle, we have the arming screws for the lower stage, which are easy accessible from the ground, so you don't have to go on any ladder or something to arm the lower stage. In the upper stage, we used pull pin switches instead of arming screws, as you arm the upper stage ignition from a distance instead of being close to the vehicle, and of course standing on a ladder and arming a rocket isn't the nicest thing to do, so we made sure that you can arm the upper stage from a safe distance. The whole rocket has a liftoff weight of roughly 59 kilograms, of which are 25 kilograms structure and roughly 4 kilograms payload. The payload could have been developed lighter from our side, but unfortunately the rules of SAC didn't allow us to develop a lighter payload, so we needed to add additional boilerplates, which we wouldn't have needed for the successful experiment. For the IREC 2025 vehicle, we're looking forward to a velocity of roughly Mach 2.5. Which would be the fastest vehicle of WARR rocketry yet. Thank you for watching. I hope you liked the video. Make sure to hit that like button and subscribe to see all the upcoming videos, because there are a lot of very interesting parts we want to show you and developments we want to share with you. So make sure to come again.